Hello viewers, I'm Kausalya. Today's topic is state space representation using phase variables. So as we all know what is meant by state space representation, right? So here the phase variables are nothing but they are the particular state variables, right? And these state variables are obtained from the system variables and its derivatives, right? That is, phase variables are nothing but state variables, and those state variables we get from the system variables and the respective derivatives, right? Now, usually you see the state variable used is the system output. We are considering the system output as the variable, and the remaining state variables are nothing but derivatives of the output, right? And the next thing is, if the system model is already known in the form of differential equation or transfer function, then the state model using phase variables can be easily determined. That is, if a system model, that is, if we are having a differential equation of a system or transfer function of the system, then it is very easy for us to analyze the phase variables, right? Here, three methods are used for modeling a system using phase variables. Right. Now we are going to discuss about method 1. So again, this is a general representation. Right. So consider the following nth order linear differential equation relating the output to the input of a system. So here we are having a differential equation, right? The differential equation relates input and the output. Here input is nothing but u of t and the output is nothing but y of t, right? So this is the differential equation. Okay, this is a general form of representing a differential equation for this analysis. So here, as we know, u is the input and the respective y is the output, right? Now you see, by choosing the output y and their derivatives as state variables, we get y is selected, y and its respective derivatives are selected as state variables, right? Therefore, we are going to assign different values for different values of y to some x. So here you see, we are taking x1 as y, x2 as y dot and x3 as y double dot, and here xn is n minus 1 times of y, and finally xn dot is y to the power n dot. So here you see y is x1, when you differentiate y that is equal to x2, when you double differentiate that is x3, and here so simply we are writing the expression as here xn means y to the power n not to the power, that is y is differentiated how many times, that is indicated here, that is n minus 1 dot. You see here for example n is 3 means x3 which is equal to y n minus 1, 3 minus 1 is 2, so 2 dot, right? So finally here xn dot is equal to yn dot, right? Now we are going to substitute the state variables in our basic equation, right? So here we know, right, y to the power n dot is replaced as xn dot plus similarly a1 as such here, and y to the power n minus 1 dot is nothing but it is equal to xn, right? Likewise, just substitute the values here which is equal to b times of u. And when you rearrange the expression, that is we want only x1 to the power dot, sorry, xn dot, unknowingly I am saying as power, that is differentiation of xn, right, which is given by this expression. Now we are writing it in the form of state equations, right? So when you write it as state equation here, so here the state equations are x1 dot is nothing but here it is equal to x2. So here look at this expression, right? That is x1 dot. When you differentiate x1, what happens here? Here it becomes y dot, right? Just I'm writing x1 dot will be equal to y dot, right? That is, I'm differentiating on both sides. So this y dot is nothing but this is equal to x2, right? We had already assigned. So here we can write this x1 dot is equal to x2, right? So this is what we had done there, right? This is the reason why here x1 dot is equal to x2. Similarly, x2 dot is equal to x3, and it goes on, and finally we are having an expression for xn dot, right? Now we are writing this in the form of a matrix. So when you write it in the form of a matrix, you see here, this is our matrix form, right? x1 dot, x2 dot, it goes on, right? Sorry, here it is xn dot, right? And here when writing expression as usual, you see x1 dot is equal to x2 here. So here the coefficient of x2 is made 1 and the remaining terms are 0. And again x2 dot is equal to x3. So coefficient of x3 is 1, right? So it is 1 and the remaining terms are 0. So likewise you just arrange the terms, and here we are having a matrix like this, right, which are multiplied by the respective x1, x2, and it goes like this, plus again only to the xn dot. In this expression we are having input value, right? So in the rest of the terms everything is 0, and here the coefficient of u is b. So here it is b, which is multiplied by this u matrix, right? So generally we can write this expression as x dot is equal to ax. So this is your A matrix, this is your x, plus, and this is your B matrix, and which is multiplied by the u here, right? So generally it is written as x dot is equal to ax plus bu, right? So here when you look at this matrix A, right? So this is our A matrix, right? So when you look at the matrix A, it has 1 in the upper of diagonal, right? So these are the diagonal elements. So in the upper half they are having 1, right? And the last row of this matrix consists of the negative coefficient of the differential equation, right? So here you see everything is in negative, and these are all the coefficients present in the differential equation. So here you see this is our differential equation, right? Here coefficient of x1 is minus an. So here minus an. Likewise coefficient of x2 is minus an minus 1, and so here minus an minus 1, right? So likewise you see here all the elements are negative. So this is a special type of matrix, and this form of matrix is known as Bush form or companion form, right? That is a matrix whose upper off diagonal elements have 1 and the remaining elements are 0, and the last row of the element has negative coefficient of the differential equation. Then this type of matrix is known as, it is of the form Bush form or companion form, right? Now we are going to the output part, right? And here the output is nothing but y, and the value of y is equal to x1. We had assigned already, right? So while representing it in the form of a matrix, you see y is equal to the coefficient of x1 is 1 here. So 1, the rest of the elements are 0, which are get multiplied with x1, x2 up to xn. So the general representation of this y matrix is y is equal to c into x, right? So here comes the end of the video. If you have any doubt, let me know in the comment section. Thank you.